So we'll look at formulas for how to do these later, but first we're going to look at how to do them informally, just basically get the equation that makes up the sequence in our head. And how I would do it informally is, I know these are going up by 2's each time, so because they're going up by 2's, this has a slope of 2. This is a y equals 2x problem. Just like this problem, they're going up by 3's, so this has a constant rate of 3, so this is a y equals 3x problem. And now that I know what it's going up by, I have to see if that works. So my first term, second term, third term, fourth term, fifth term, sixth term, if I do what I said, I take 2 times x, I would get 2, 4, 6, 8, 10, and everything would be, looks like one number too high. So if I just were to subtract 1, I could get the right answer. So the formula for this sequence is y equals 2x minus 1. In this other sequence, if I took my x values 1, 2, 3, 4, 5, and I times them all by 3, so 3x here, I'd get 3, 6, 9, 12, 15. And in this case, I would just be one number too small, so I'd have to add 1. And that would give me all the right answers. 3 times 3 plus 1 is 10. Another way to think about sequences informally is just what do you do to the x to get the y? Like what would I do to 1 to get 1? What would I do to 2 to get 2, 4? And what would I do to 3 to get 9? And if you recognize them, it can be a lot easier to just say, oh, here's the formula. Y is equal to x squared. And to not have to use all of the fancy new rules that we're going to be learning. Like on this one, it's harder to think about because they don't have a common difference. Let's see, 1, 2, 3, 4, 5. What do I do to the x's to get the y's? Well, these don't have a common difference. Like this has a difference of 2, and this has a difference of 3. This has a difference of 4. So because they don't have a common difference, I can't just figure out what the slope is. So if I can't figure out the slope, sometimes trying doubling or tripling would work. So instead I'm going to go 2, 6, 9, let's see, 2, 6, 12, 20. And if it's not a what do I add sequence, see, well, could it be a what do I multiply sequence? This is 1 times 2, this is 2 times 3, this is 3 times 4, and this is 4 times 5. So if I look at each of these, I take the number, like 2, and I times it by 3, that gives me 6. Take the number 3, and I times it by 4, that gives me 12. So I could take the number, times it by one number bigger. Okay, that would give me the 2, 6, 12, 20, and so if I just were to divide that by 2, I'd have the sequence. So y equals x times x plus 1 divided by 2. In this assignment, you'll be looking at both recursive and explicit definitions of sequences. So let's first of all talk about the explicit definition. An explicit definition gives you a formula that will identify each term in the sequence. And so like the first term is 4, and the next term is 4 plus 3, and the next term is 4 plus 3 more, and the next term is 4 plus 3 plus 3 plus 3 more, that's 13. And if I want to get 16, it's 4 plus 3 plus 3 plus 3 plus 3. So I take the first term plus 3 times the number of terms minus 1, because first term, second term, third term, fourth term, fifth term. See, when I'm at the fifth term, actually I'm only using 4 3's. So if I were to take 4 plus 3 times 5 minus 1, that would give me 16. Okay, so your explicit definition is your nth term a sub n, is equal to your first term, a sub 0, plus the difference between each term times n minus 1. I think it's easier to work it out sort of without the formula, although you can memorize the formula. Now let's take a look at the recursive formula for the same exact problem. The recursive formula is this. It's a sub n is equal to a sub n minus 1 plus 3. And what I'd like you to think about is seeing the a sub n as the term and a sub n minus 1 as being the previous term. So this is sort of like saying how you would describe this. If I wanted to get 7, I would take, so if I wanted to get 7, I would take the previous number 4 and add 3. If I wanted to get 10, I would take the previous number 7 and I would add 3. So if I wanted to get 16, I would take the previous term, 13, and add 3. So this definition, the recursive definition, is how I would get the last term from the previous term. So when you're reading this, this is saying the first term is 8, so they're giving you the first term, and to get each term in the sequence, you take the previous term and you add 5. So the first term is 8, second term is the previous term, which would be 8 plus 5, which would be 13. To get the next term, you take the previous term, 13, you add 5, you get 18. To get the next term, you take the previous term, 18 plus 5, 23. To get the next term, you take the previous term, 23, add 5, you get 28.
Thank you.
So what we're looking at right here is the recursive definition. If you had to take this problem and get the explicit definition, we're starting off with 8, and then you're taking 8 and you're adding 5, and then you're taking 8 and you're adding 5 twice, and then you're taking 8 and you're adding 5 3 times. So the explicit definition would be the first term, 8, plus 5 times, first term is 8, second term is 13, third term is 18, fourth term is 23. So if you look right here, to get the fourth term, you need 3 5s. So this is number of terms minus 1 power. And that's how you get the last term, a sub n. This is the explicit definition. Let's take a look at this sequence both explicitly and recursively. First of all, let's verify that it does have a common difference. I have to subtract 3 each time. And so this is an arithmetic sequence. If it's an arithmetic sequence, I'm going to figure out, to get the next term, what do I do to the previous term? So in this case, like to get the 4, I would take the 7 and subtract 3. So to get the nth term, I would take the previous term and subtract 3. This is my recursive definition. So let's take a look at the same problem with my explicit definition. My first term is 16. My second term is 16 minus 3. My third term is 16 minus 3 minus another 3. My fourth term is 16 minus 9, which is 7. So I add in term numbers, first term, second term, third term, fourth term. So to get the fifth term, I take the first term and I have to have 4 negative 3's. So my explicit definition is a sub n is equal to 16, my first term, plus negative 3 times n minus 1. Sometimes you'll get to problems and they don't have a common difference. Like if I try to figure out a common difference here, first I add 4, and then I add 12, and then I add a big number. When you realize they don't have a common difference, you might start looking for other patterns. Like they don't have a common difference, but could I multiply by something? Like this is times 3, and this is times 3, and this is 18 times 3 is 54. So if they're all multiplied by the same number over and over again, it's called a geometric sequence. Let's first look at it explicitly. So first term, second term, third term, fourth term, fifth term. My first term is 2. And my second term is 2 times 3. That gives me 6. And my third term is 2 times 3 times another 3. That gives me 18. And my fourth term is 2 times 3 times 3. That gives me 18 times another 3. That gives me 54. And so if I were to find the nth term, all of these start off with a 2. So that would be the first term, 2, times the ratio, what I'm multiplying by each time. In this case, my ratio is 3. And then I have to stop and think. The fourth term, I need 3 3's. The third term, I need 2 3's. The second term, I need 1 3. So it's 3 to the n minus 1 power. And so your formula for geometric sequences, the explicit formula, is going to be a sub n is equal to a sub 0, the initial term, times the common ratio, that's what you're multiplying by, to the n minus 1 power. So now let's take a look at the same problem, but I'm going to define it recursively. So again, this is my explicit formula. When I define something recursively, I define it in terms of the previous term. Like if I were to take, in order to get the 6, I would have to take 2 times 3. In order to get the 18, I would have to take the 6 times 3. So in order to get the next term, I would have to take the previous term and times it by 3. So the recursive formula for this one is a at minus 1 times 3. If just every time you see this, you think either the next or the last, depending on the question, and every time you see the n minus 1, you think, well, that's just saying previous. That will go a long ways to helping you straighten out what these formulas mean. Here's an example of a recursively defined geometric sequence. This one is saying that to get the next term, a sub n, I have to take the previous term, a sub n minus 1, and I need to times it by half. So here's my first term, 64. To get the next term, I take 64 times it by a half, that's 32. To get the next term, I take 32 times it by a half, I get 16. To get the next term, I take 16 times a half, I get 8. 8 times a half is 4, times a half is 2, times a half is 1, times a half is a half. It keeps going like that. So there's your recursive definition. Now let's look at an explicit definition of the same sequence. I take 64, and then I times it. That's my first term. To get the next term, I have to take 64 and times it by half. So I have 64, that's my first term. 64 times a half, that's my second term. 64 times a half, that's my third term. 64 times a half, that's 8. So look at these in terms of term numbers, 1, 2, 3, 4. To get my nth term, I have to take my first term, times it by a half, but since I need 3 1/2 to get the fourth term and 2 1/2 to get the third term, this has to be to the n minus 1 power. Or let's say I wanted to get 1, 2, 3, 4, 5 to get the sixth term. So to get 2, because 2 is the sixth term right here, I would take 64 times 1/2 to the 6 minus 1, fifth power. 64 divided by 32, that's 2. That works out. And last, you also need to be able to identify if sequences are what's called convergent or divergent. Divergent basically means they're headed to positive infinity, they're headed to negative infinity, or they go back and forth and back and forth and back and forth and back and forth. So a sequence that's convergent will get smaller and smaller and smaller and approach a single number, like that example we just did where we kept timesing by a half. If you take half of a half, you get a fourth, and half of a fourth, and you get an eighth, and half of an eighth, you get a 32nd, and half of a 32nd, you get a 64th. And this is just going to keep getting closer to 0. So this is an example of a convergent series, whereas the other one, where we are timesing by 3 each time, timesing by 3, timesing by 3, it just is getting bigger forever, and so it's headed exponentially, so it's a divergent series. You can really boil these down to, does the limit as x goes to infinity approach a number? If it approaches a number, like if it has a horizontal asymptote, it's a convergent series. Or if the limit is heading up forever or down forever, that would be divergent.